Good evening, ladies and gentlemen. My name is Joshua Rasera, and I'm a PhD student here at the Royal School of Mines of Imperial College. Today, I'm here to talk to you about space mining, the future of human space exploration. You're in darkness, and you wake up. You feel groggy, you feel kind of weird, and in a daze you wonder, where am I? Well, today is March 14th in the year 2030. You are an experienced mineral processing engineer from Earth, and you have just made the absolute biggest move of your entire career, to the moon. The moon is our closest celestial neighbor. It's about 400,000 kilometers away, and it has hugely impacted human society since time immemorial. Cultures, religions, lore, and fascination have all been greatly influenced by the moon. In the year 2030, the moon is the main staging ground for launching resupply missions and future astronauts to the newly settled Martian colonies. It is also the main location for all of our launches for deep space missions and is supporting people in a variety of different industries from agriculture to mining to tourism. So you're thinking, cool, I always wanted to be an astronaut, but why did I end up moving here? So, you see, you have to think back to the year 2019, and at that time, the government of Luxembourg, PricewaterhouseCoopers, and the European Space Agency forecasted that by the year 2040, space resources would be about $190 billion a year industry. And a couple of years before that, the United Launch Alliance, which is a joint venture between Lockheed Martin and Boeing in the United States, said that they would pay up to $3,500 per kilogram of fuel made available in space. So, naturally, the company you work for, Lunare Resources, is one of the first companies to operate on the moon and be a part of the lunar oxygen mining value chain. Now, oxygen is incredibly important for this lunar economy, namely because it provides you, a human being who needs oxygen to live. It also is a key ingredient in rocket fuel, allowing us to continuously refuel our spaceships to go to our Martian colonies and beyond. So now you're thinking, well, this seems very lucrative. I think I made a good choice. And you did. But you still have one question. What's my job? That's a very good question. So as I said, Lunare is a part of the oxygen mining value chain. And you can see that whole chain here. However, this is a very big process, and they don't do everything on their own. Instead, they focus exclusively on this beneficiation step. Now, in the case of Lunare Resources, in the case of the moon, there are usually three main steps: comminution, or the reduction of size and liberation of certain minerals; size sorting, in order to get an exact range of sizes for the particles that you're trying to pass on; and then enrichment, where you increase the concentration of a particular mineral in the feedstock that you're passing forward. However, on the moon, due to the nature of the stuff that you're mining, we can actually ignore the comminution phase, and that's what Lunare has chosen to do. And I'll explain this more later. But for now, just know that your company is responsible for size sorting and beneficiation tasks. So, as a part of this overall value chain, Lunare Resources is responsible for providing an ideal feedstock for its downstream customer, Roxygen Systems. Roxygen Systems uses a hydrogen reduction technology that was developed by NASA way back in 2008 to produce oxygen from ilmenite. And so, Lunare, a requirement from Roxygen to Lunare is that they must provide a specific feedstock with the right grain size and the right concentration of ilmenite, otherwise the hydrogen reduction system will not work properly. And you can see here one of the original testing rigs that NASA was able to develop all those years ago. So you're thinking now, well, no problem, I've got tons of experience in mineral processing, so I'm sure we can just do what we do on Earth. If only it were so simple. Unfortunately, you've forgotten about a couple of key things, the first of which is the lunar environment. And to be honest, it's extreme in every sense. For one, there's no liquid water at all on the surface. While there might be ice at the poles, there is no free-flowing water anywhere, which means we can't use water as a process material. The moon doesn't have an atmosphere. It is a hard vacuum and a thin, dusty exosphere caused by static electric forces that levitate dust off of the surface by about a meter, which means you also don't have any air or nitrogen or any other gases that you can compress and use as a process fluid as well. There are wild temperature swings in the surface of the moon, At the equator, the daytime high can reach up to 127 degrees Celsius, and at night, the temperature can drop down to minus 173 degrees Celsius. And while you're spending time on the moon, during some of your leave, if you decide to go visit the water mines in the North or South Pole, you could experience temperatures within the permanently shadowed craters of up to minus 238 degrees Celsius. This is incredibly challenging for temperatures. Made worse by the long day-night cycle. One lunar day is equivalent to 13.5 Earth days, and the same for the lunar night. This means that while you might have ample energy available to generate power during the day, as soon as the night comes around, you have to be able to keep powering all of your equipment. And so you need to have sufficient energy storage and the capability to keep your equipment in operating state during the cold, long night. Last but not least, the gravity is very low, about a sixth of that of what you'd expect on Earth. This means that any processes that you use that are dependent on gravity as a force, anything with density separations and so on and so forth, become that much more difficult because the gravity force is that much lower. And in addition to the lunar environment, we have to deal with our feedstock, the regolith, or run-of-the-moon material, if you will. The regolith covers the entire surface of the moon in thicknesses ranging between a few centimeters to tens of meters deep. It's highly cohesive, it's electrostatically charged, it's very much abrasive, and it's very dense, especially beyond 1 meter in depth. It's also incredibly fine. The average grain size is roughly 72 microns, and this explains why we don't really need a combination process for lunar industries. And now, you're probably wondering how this material ended up forming, because on the moon we don't have any fluids. There's no erosion as we would experience on Earth. Well, the thermal cycling that the moon experiences with the day-night cycle, going between those highs and lows, causes the rocks to expand and contract. And over the billions of years the moon has existed, these rocks have formed very fine dust. In addition, meteoroid impacts from very large asteroids and comets all the way down to micrometeoroids less than millimeters in diameter end up smashing into the moon and cause this breakdown. This creates very sharp, angular, and very aggressive and abrasive dust that you have to deal with. This is what the regolith looks like when you analyze it up close. And you can see the major phases include plagioclase, pyroxene, olivine, and ilmenite, which is of course important for our downstream presence of oxygen, and a bunch of other minor phases and new phases that don't even exist on Earth. However, how the regolith is actually composed and what it looks like is incredibly important. It's primarily composed of rock and mineral fragments. However, there are other components as well, including pyroclastic glass beads that were formed through ancient lunar volcanism. In addition, there are breccias that are formed through massive meteoric impacts, and agglutinates, which are unique to the lunar environment, that are formed when micrometeoroids traveling at many kilometers per second strike the moon at the velocity that they're traveling through space at. When this happens, the local material liquefies, but because of the radiation environment in space, it instantaneously solidifies again, forming a glassy structure with this angular, sharp edges that you see here. And this is what causes a bunch of problems when you're using any moving parts. So this is something that you really have to watch out for. So now you're thinking, whoa, they can't use water? Then what could they possibly use instead to do all this mineral separation? This is what I based my career on. Well, now I'm going to have to ask you to really dig deep and flash back to the year 2019. Brexit's happening, the Kardashians are popular, the 90s are coming back for some reason. So just try to imagine that today is the 14th of March 2019. Just try. Now, there are some researchers in Imperial College who are developing new dry processing technologies. And now you're thinking, hold on, wait, thinking back to 2019 is hard enough, but what is this dry witchcraft that you're talking about? Mineral processing needs water. Well, basically dry processing is any excavation, haulage, comminution, size sorting, or enrichment process that is water-free. Seems simple enough. And if we focus explicitly on dry beneficiation, there are really three main variants. Ones that use gravity as the main separating force, ones that use magnetism as the main separating force, and ones that use electrostatic forces as the main separating medium. So, back in 2019, dry process were some of the scenes of black art. Companies would do strange and wondrous things, including smoking them with a variety of different chemical smokes and dousing them with light diesel, and without really fully comprehending the underlying physics of why they were doing this, but they just knew that it worked. However, this was very much limited to a narrow industry that mostly focused on mineral sands and enrichment. However, water-based methods prevailed and were mostly used, even including the magnetic gravity methods. So you can see here all of the processes that we used to use on Earth, and still use on Earth, are heavily water dependent. But the goal that Imperial called it, the research that Imperials were aiming to do, was to demystify, optimize, and redesign a lot of these new separation methodologies using dry processes instead. So by manipulating gravitational and electromagnetic forces, they were able to develop new dry mineral processing techniques. And now this is your new operating window. So by the year 2026, your company, Lunare, was formed, and they began using these dry separation techniques that were developed by Imperial's research and development a few years previously. So now you're thinking, wow, well, I mean, this is an entirely new world. This isn't something that I've ever done before. But you're looking forward to it, and you're really hoping that Lunare has a very good training program to bring you on board and bring you up to speed. But fortunately, they do, and so you will learn all you need and more once you get to the moon. So to conclude, ladies and gentlemen, the vision of the future that I've painted for you today is very optimistic, but we have to realize that rehashing the wet technologies that we use in terrestrial mineral processing just will not cut it on the moon. They won't work. The environmental and material conditions that we have there are not suitable for the technologies that we have today. Therefore, we really need to approach this industry by changing how we look at the fundamental physics to really understand how separation actually occurs and what changes that we can make to it in order to develop new technologies for this new environment and new materials. So, as I said before, the vision that I've painted is very optimistic. It's very forward-looking. And I think that this quote from the late Reverend Norman Vincent Peale actually sums it up very well. He once said, "Shoot for the moon. Even if you miss, you'll land among the stars." And I think that if I can have passed along anything to you today, it's that you're dreaming big about the future of space resources, are thinking about new technologies and new ways to do things, and are excited about the world that is to come. However, I do think we need to paraphrase the Reverend a little bit and change this quotation to say, "Shoot for the stars, and even if you miss, you'll land in the moon."